Most of us have probably seen Lewis structures at one point or another in a chemistry class. These are when we write out the atoms that make up a given molecule and throw a bunch of dots and sticks around the atoms. It's a little more elegant than that, but you get the idea. Before we dive into the intricacies of drawing these structures, let's first discuss what Lewis structures are as opposed to what they are not. A Lewis structure is a very simplified representation of the valence shell electrons in a molecule or an ion. These depictions are used to show how the electrons are transferred from one atom to another in ionic compounds or shared between atoms within a molecule. Electrons are shown as dots for lone pairs or as a line for bonding electrons between the two atoms. Lewis structures, however, do not directly explain the geometry of molecules, how bonds form, or even tell us much about how electrons are shared in the bonds we draw between the atoms. This is an extension of a simple, extremely limited theory on electronic structure. These are the stick figure drawings of the chemistry world, where all parts are about where they should be, but the 3D depth and shading of a realistic depiction just aren't there. Understanding the information conveyed by a Lewis structure is an important skill, but first we need to know how to draw one. Fortunately, there are some rules to guide us through the process, which we'll exemplify using carbon dioxide. First, draw the atoms of the molecule in the proper position if you know them. Usually, the atom that can make the most bonds is in the middle of simple molecules. Molecules made from more than two elements can be more difficult to guess, since the bonding pattern may not be obvious. For these compounds, do your best to determine which atom is the central atom and then arrange the other atoms around it. Carbon is a common central atom. Hydrogen, with its inability to form more than one bond, is never a central atom. When in doubt, note that the atom with the lowest electronegativity is very often central. And don't stress about memorizing a bunch of rules for central atoms. Much of this will come with practice, and it will rarely be central to a test question. Returning to our example, carbon will be the central atom of CO2. After the parts of the molecule are drawn, determine how many valence electrons must be present in the entire molecule. You can find the number of valence electrons associated with a given atom by using the periodic table. Here, carbon has 4 valence electrons, while oxygen has 6, yielding 16 total valence electrons for CO2. Third, the atoms must be connected by at least one bond, so begin by drawing single bonds to connect them. Next, determine how many valence electrons have yet to be assigned. We know the compound has a total of 16. Subtract 2 for each single bond, and we see that we now need to pass out an additional 12 electrons. Place these lone pairs on the peripheral atoms in an attempt to give each a full octet. This is where we arrive at a problem. Our compound has the proper number of electrons, and the 2 oxygen atoms have complete octets, but the central carbon atom only has 4 electrons. From our previous video, we know that carbon is one of the 4 elements that nearly always has to have a full octet in stable compounds. In cases like these, start changing lone pairs on the peripheral atoms to additional bonds to the central atom, one bond at a time, until as many atoms as possible have proper octets, ideally all of them. Now, I know what you're thinking. This is too easy. We want a bit of a challenge. We love tough chemistry questions. Okay, ask and you shall receive. Let's draw a Lewis structure of carbonic acid, H2CO3. Same as before, we need a central atom. Carbon is our winner, as it's the least electronegative atom here that can accommodate more than one bond. The 2 hydrogen bonds can only support one bond each, so they're stuck somewhere on the perimeter of the molecule. This means that the 3 oxygens will be the ones bound directly to the carbon. So our initial structure looks something like this. Next, let's see how many valence electrons we have. Each hydrogen comes with 1, carbon brings 4, and each oxygen has 6. The math's a little tougher here than last time, but still not bad. 2 times 1 plus 4 plus 3 times 6 equals 24 valence electrons. The structure we began with has 10 electrons accounted for in its bonds, so we need to distribute 14 more. the oxygens with hydrogens on them can still take 4 more each, and the remaining oxygen can take 6. Filling in these octets on the oxygens leads us to the next structure. While the oxygens and hydrogens look happy, carbon is having a bad time. Currently, it only has 3 bonds for a total of 6 valence electrons, which makes it a carbocation. As everyone who's taken OChem probably remembers, carbocations are about as stable as a pregnant hippo on a unicycle juggling bowling balls. So one of the oxygens needs to help the hippo out by converting their lone pair into a bond to the carbon, which leads us to the final structure, and to a much happier hippo.